So let me start by saying a few words about a very important invariant that has already appeared many times, that many of you know very well. Some of you know it much better than I, but let me speak about that now. Which is the, and I want to speak about that because in my lecture today it's going to appear quite a lot, and that's very important on itself. So let me say a few words about the Miller number. So we can consider f from Cn plus 1. You see? In fact, I only need to be defining a neighborhood of the origin. It's an holomorphic function. We are isolated. Good. Like that. Well, we are critical point at C. Here. Then we know there is a minimum vibration in a view. It's already spoke about it. So we have the special fiber with minus 1 and 0. We take a mirror sphere around it. So inside we have a conical structure. We have F. We have C, we have the origin, and then we take a sufficiently small circle around the origin, so that for each point within this disk, the corresponding fiber intersects this sphere transversally. Okay? That such a disk exists is an easy exercise to show when we have an isolated critical point, and it's a consequence of a deep theorem when we have only isolated critical value. Okay, but we always have it. So we take a sufficiently small disk so that all the fibers here are transversal to this sphere. And then the Miller vibration is taken by taking this cube minus the central fiber and projecting it to the disk minus the point. Okay, and that's a local extremal vibration. And sometimes we take only the boundary of it, which is mapped into the boundary circle. That's also called a Miller vibration, whatever you want. Okay, and one of those fibers, the typical fiber, is f minus 1 of t sufficiently close to 0, cap into the open body. Okay, this is the typical fiber. And the theorem says, or Miller, that this has the homotopy type of a bouquet. I never remember bouquets like this or
no, to hear without.
Thank you. Okay. It's a bouquet of spheres. So this is defined by one equation. So this has complex dimension n, intersecting the above set has complex dimension n, so real dimension 2n, and the theorem is that this manifold of real dimension 2n has the homotopy type of a bouquet of spheres of middle dimension. This means that you take a disjoint family of spheres and then you put them together in one point. So that's like a bouquet of flowers, but this is a bouquet of spheres. Okay? How many? Some number. That number is called the Miller number. Okay? And exactly the same theorem holds when you have a complete intersection. If you take, instead of one function, you take f1 up to fk holomorphic functions such that Sorry. I said something which is not correct. Up to this point, everything is correct. To come to this theorem is if F has an isolated critical point. Okay? And in fact, one can say more. It's a theorem, later theorem by Milnor in almost all dimensions and completed by Lea and Perron, that F is actually homeomorphic to a ball of dimension 2n to which one attaches handles of middle dimension. As many handles as the Milnor number. And when the singularity, the critical point is not isolated, you still have a Milnor fiber, but the topology is more complicated. It's homeomorphic to a ball of dimension 2n to which you attach handles of many dimensions. How many dimensions? As many as some numbers which are called the Len numbers introduced by David Massey. Okay? But I will not come into that. So, in this case, now, in the case of complete intersections, one has if. So, if you have this, and and the variety V has dimension n, and it has an isolated singularity. In other words, if the critical set of this function intersects the special fiber only at the origin, in the neighborhood, then we say that that's what is called an isolated complete intersection singularity. And then in that theorem, in that case, one has a similar theorem. Well, instead of the point here, one has to remove the critical values, the discriminant, and then one has a cube that maps over the complement of the discriminant, and one has a similar vibration, and that was proved by Ham. All of that is rather easy to prove. The very interesting thing of Ham's theorem is that in that case, the same theorem is true. The Milnor fiber has the homotopy type of a bouquet of spheres of middle dimension. It is not, as far as I know, there's not such a nice description for complete intersections as saying that it is homeomorphic to a ball, blah, 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 blah. So we have this. Now, in the case of hypersurfaces, when k is 1, the minimum number can be computed algebraically in a very nice way. We take the holomorphic functions in the empty space at 0, you divide by the Jacobian ideal. You divide by the Jacobian ideal, you take the dimension of this algebra, and this is a linear number. Okay? So this thing, which is defined in a very topological way, has this very interesting, very powerful algebraic interpretation. For complete intersections, there is something in that spirit. It's called the Legge-Euler formula. It is not as simple as this. It's given by something. Okay, I won't come into that. I don't need to come into that. Okay? So this is the linear number. I see a very important invariant which appears in many places in singularity theory and in other subjects. Okay, so let's keep this in mind and let me go back to the definition of the GSB index. Let me do it. Yesterday I did it for hypersurfaces. Let me do it for complete intersections. So we have this setting. Let me go here. Suppose we have a isolated complete intersection. So this is V with -1 of 0, which has an isolated complete intersection singularity at the origin. Let E be a continuous vector field on V, the origin. That means the restriction to V of a continuous vector field in the empty space, and with isolated singularity of the vector field at the origin. A equals B is equal to the sphere, the link, to the singularity. Okay? Now, notice that since V is a complete intersection, the gradient vector field gradient of F bar gradient of F bar, let's say, gradient of F2, let's say, up to the gradient of Fk, let's say, are all linearly independent and orthogonal to V at each point in the link. Okay? So if we have a similar variety, we take an intersection with the sphere. This is the link, and at each point here we have these k vector fields which are all orthogonal to this variety, which is non-singular here. And we have it at all points, in particular. Now, since these are linearly independent, they define a k frame at all those points. And since they are normal, so this is a K-frame which is canonically given. It comes out of this, from this information. If now you have a vector field which is tangent to the variety, then together you have a K plus one frame. So V, together with these gradient vector fields, defines a map from K, which has dimension 2n minus 1, into the Stephen manifold of K plus 1 frames in Cn plus K. Okay? And then, as I said yesterday, it is well known, easy to show, using well-known results, that all the homotopy groups of this variety vanish, and the first one, which is non-zero, is exactly in this dimension. So this map has a degree in set, which can be defined in several ways. For example, you take the homology, the top homology of this, let's say isomorphic to the integers, and you see the generator, how many times the generator goes in this dimension. That's one way to define it. Okay? And then the GSV index is the degree. So GSV equals the degree of this map. Let me explain a very geometric, very nice way to determine this degree. Here we have a ring of fiber, fiber, we choose one sufficiently close. And then, just as I explained yesterday, well, the tangent vector field here can be pushed. So the intersection of this fiber with the sphere, this is the boundary of the ring of fiber, that's isotopic to K. And this vector field can be moved to a tangent vector field in the neighborhood of the minimum fiber. So everywhere in the boundary we have this vector field. Okay? And the gradient vector fields are nowhere zero on the whole minimum fiber because it's all a no critical level. So all these vectors are well defined and transversal everywhere at each point of the minimum fiber. Okay? So now try to extend this K plus 1 frame to the interior of the minimum fiber. The K frame on the interior. But we already have K of them. And they are orthogonal to this guy. So to have one more, we only need to extend this one as a tangent vector field, tangent to the minimum fiber. Okay? And then we know that has local indices given by Poincaré-Hopf. You add them up, and you get this number. Okay? So we're saying, what I said yesterday, that this number defined in terms of homotopy, algebraic topology, it is the Poincaré-Hopf index of an extension to the nearby minimum fiber. It's just for free, even there. Okay? Now, well, and as I also mentioned, we mentioned that for complete intersections, this index it coincides with the homological index that I defined yesterday. And thus we have an algebraic characterization. In particular, suppose V is smooth at C. In other words, there is no critical point. It's a regular point. A very simple case. Then we not only that this is not have to see that the homological index is just the same as the dimension of O of n plus k. Taking a coordinate chart in V around a singular point, we identify that with Cn. We take this, and this is divided by suppose V is smooth at V and K equals 1. Yeah, it is true also, but I don't want to get confused. So taking local coordinates is the partial of n with respect to C1 of the partial of n with respect to set n. The local coordinates in V. Okay? And so this is always greater or equal to 0. And if there's this is 0 when the vector field has no singularity. If there is singularity of the vector field, we have greater than 0. So the index is always positive for polymorphic vector fields. This is true only for polymorphic vector fields. We mentioned yesterday that if V is radial means that you take the vector field and you take the intersection of you take any sphere center at the singular point, then at the intersection points with V, the vector field is transversal to the sphere pointing outwards. So suppose it is radial, then its GSD index is 1, well, is the other characteristic of the minimum fiber. And since this has the homotopy type of a bouquet of spheres of middle dimension, this is just 1, the zero Bethe number plus minus 1 to the n times the middle Bethe number. Yes. So, and mu is always greater or equal to 0. If there's singularity, this is actually greater than 0. So this number for radial vector fields is almost always negative, except in very special. When this is even, when this is odd, and this is 1. Okay? So this is almost always negative. And for example, for all quasi-homogeneous singularities, the vector field given by the C star action is holomorphic, and then in most cases is negative. So you see that in the smooth case it is positive. Here this index can be negative, but that's okay. There's a very, very interesting theorem by Bonatti, Christian Bonatti, and Gomez-Mont. There is a smallest, but for all germs, there is a smallest bound for the index. So it can be negative, but not arbitrarily negative. So it has to be larger or equal to something. And the vector fields with lowest index are an open dense set in the space of all vector fields. All holomorphic vector fields. So smallest for the index for holomorphic vector fields. If it is continuous or smooth, you can have anything. For holomorphic vector fields, there's a lowest bound. So, for example, a natural question: if you have a singularity germ, a natural question is, what is a generic vector field? That's the definition of generic. And this raises a natural question. What is this lowest bound? The answer is I don't know. I believe this is minus 1, sorry, 1 plus minus 1 to the n times v. And second, I believe that if maybe I'm wrong, if this bound is how do you say, is reached, if there is a vector field without bound, then actually this bound is attained, weighted and homogeneous. I know that if it is weighted and homogeneous, then there is an open dense set of vector fields with this index, which is essentially the radial vector field given by this interaction. And deformations of it, perturbations of it. And also, one day I knew how to prove it when n equals 1. But now I don't remember how I did it. But I'm sure it was true. Okay, so that's all for the local situation. Now let me move to the global setting. Let L be a holomorphic line bundle over a manifold, complex manifold n of dimension n plus 1, and X defined by a holomorphic section of L. So we have a holomorphic section of this bundle, and we look at the zero set. So I will say that X is a hypersurface. Okay, the singular set of X are the points where the section is not transversal to the zero section. Where that section is transversal to the zero section, we are at these blue points. And when we don't have that transversality, we get singularities. Assume X has only isolated singularities. Let V be a continuous vector field something like, let me call them Q1 up to QR, or some R, final number. N compact, name N compact. Let me be a continuous vector field on X with isolated singularities. Okay, so it will be similar. So we have a singular variety. Okay, so the vector field will be singular at these points, and perhaps it will be singular at some of these smooth points in X. Okay. Or if you want, you can do it the other way. Choose one gel at each singularity with isolated singularity. Then if you chop off these cones, you have a manifold with boundary and a vector field with no singularities on the boundary. Okay. You can always extend it to interior with isolated singularities. Okay. And now you can define a total GSB index. What is it? The sum of the indices at each point plus the Poincaré-Hopf indices in the interior. Okay. Easy exercise, trivial exercise. That total index does not depend on any of the choices. depends only on x. Okay? Total GSD index does not depend on choice of capital X. That means if is an invariant of X, what is it? Suppose there were no singularities of X. Suppose X is smooth. Then it is a compact complex manifold. And then we have a vector field with selected singularities in a compact manifold, and we know that in the total sum is the only characteristic. Okay? Or in other words, is the top Chern class evaluated on the orientation cycle. Okay? So as you see, I'm starting to move towards Chern classes. Okay, so in this case, this index is the top Chern class of the tangent bundle when there is no singularities evaluated on the orientation cycle. When we have singularities, theorem, Suwa, and myself, I remember in the 90s, I don't remember the year. This total index. The first part is very easy to prove. The most interesting is going to be the second part. Is the GSD of X, which is a independent of vector field, is going to be just the only characteristic of X plus minus 1 to the n times the sum of the local middle numbers at the singular points. Okay? And that's really very elementary. That's differential topology very easy. That's very easy. What was not so easy is to prove something that I am going to state it, and then I'm going to say what this is. This is the n Wilton-Johnson class of X evaluated on the rotation cycle. This is top Wilton-Johnson class. Okay, what are these classes? Well, this is one extension of the concept of Chern classes for singular varieties. Let me tell you how to define that. It's a little formal, but it's more or less easy to define, and they are very computable. Let me define the Fulton-Johnson classes. In the setting we have here. In the setting we have X defined by a section of a line bundle and so on. Suppose X is smooth in M and defined by a section, a holomorphic section of L. Okay. Then we have a complex manifold M of dimension n plus 1. And when we have this, we have somewhere here a smooth submanifold X. this situation, just elementary facts of differential topology, just tell us the following two things. Differential topology is elementary. There are two things. One, the normal bundle of X in M is isomorphic to the restriction of M to X. And two, the tangent bundle of M respected to X splits C infinity, not holomorphically, as the direct sum of L of X, the normal bundle, plus the tangent bundle of X. I didn't mention, but I did mention that you have chain classes. Whenever you have any bundle over some decent space that has chain classes. Okay? And there's a very nice, the very nice property of chain classes, which is called the Whitney formula. For when you have the sum of two vector bundles, the chain classes of the sum can be expressed in terms of the chain classes of the sum of each of the pieces. In that case, let me write total chain class of Tn of X. This means this has many chain classes. Total means you take 1, which is the singular C0, plus C1, plus C2, plus C3, you take all of it. That's called the total chain class. Okay? Then the Whitney formula says that the total chain class of this bundle is 1 plus C1 of L restricted to X. This is the total chain class of this bundle because this has dimension 1, so it only has one chain class, times the total chain class of the tangent bundle of X. Okay? Now, chain classes, remember, there's one class in each dimension, and there are elements in the homology. So when you take this is an object which naturally lives, it's a polynomial which lives in the homology ring, taking the sums of all dimensions. In a ring, you have inverses. So elements, it turns out that this element, because it starts with a 1, it has an inverse. And then you can do the following very nice trick just formally. You have the C star of the tangent bundle of X. So very interested in the chain classes of this fellow. Just formally, you have that the chain classes of this guy are going to be given by this product times 1 plus C1 of M restricted to X to be minus 1. So we pass it to the other side, dividing. Okay? And then, whenever you have a manifold, you have this nice formula. Okay? Now let's go back to the case when X is singular. We define by a homomorphic section, but it is singular. We isolate the singularities or not, whatever. It's a singular variety. If it's a singular variety, it makes no sense to speak of its chain classes just like that. Chain classes, when you have a manifold, chain classes are actually manifolds of the tangent bundle. But at the singular points, there's no tangent bundle. So what are the chain classes of a singular variety? I will say more about that tomorrow. But for the moment, here we have a candidate. We don't know what this is. We don't know what the chain classes of a singular variety are. But this is a very nice bundle. It has chain classes. L is a very nice bundle. It has its chain class. This is well defined, and this is well defined. So we can define some classes by this formula. Before it was a theorem, that this were this. Now we take this as a definition. And we put Fj. Okay? And these are the Fulton-Johnson classes of the singular variety. Okay? You have, so this is a polynomial in the chain classes of n. This is a polynomial in this. You have products, so you have classes in many dimensions. So in each dimension you take those which live in H2, and they give you C1. Then the sum of all those which live in H4 gives you C2. The sum of all those who live in H6 gives you C3, and so on. Okay? And you have the Fulton-Johnson classes for singular varieties. And then the theorem I proved to Sewell is that the top one is a class in cohomology. In cohomology, you evaluate it in the orientation cycle. That's the Poincaré-Morphism. This gives you something in the homology effects in dimension 0, which is the integers. So this thing is a number, and this number turns out to be exactly this number. Okay?
I mixed. What is L?
L is the holomorphic. L is a holomorphic line bundle, so a bundle of dimension 1 over n. And you are taking a section of that gives you x. Okay? So you just for those who are not familiar with this. A bundle locally is a product. So a section is a map from a disk, locally from a disk, into the disk times C, because it's a dimension 1. And it's preserving the base point. So at the end is a map, locally a section is just a map from a neighborhood into C. Okay, so the zero set of that has codimension 1 is a hypersurface in M. So that's how we make hypersurfaces. Okay, but now you have global. Okay. Now, I will not define it, but one can show, one knows that the Fulton-Johnson classes actually are defined for all algebraic varieties. J classes are defined for all algebraic varieties. Using algebraic geometry, the second class. Roberto can explain if you want. Okay? So this side is defined in a very general setting. Now, the GSV index is only defined for vector fields on isolated hypersurface or on isolated complete intersection singularities. And this also is defined only for complete intersection isolated singularities. But we already know that this coincides with the homological index, and that fellow is defined on arbitrary isolated singularities. Okay? So one can define a total homological index. For compact varieties with normal singularities. How do you do it? Just as I did for the GSV index. At each germ, at each singularity, you choose one holomorphic vector field, whatever you want. Now you extend it to a continuous vector field from the smooth part with isolated singularities. You take the total sum, you get some number. And you show easily that that number does not depend on the choices. So it's something which depends only on the variety. So you get an invariant of the variety defined always. What is that number? That number when singularities are not isolated completely intersection singularities. When they are, you know, here we have the answer. Okay. But when you will have general singularities, no idea. I shouldn't have erased this, but have it. Definition. Let X be a compact like variety with
Hello.
before that. So here at this point, so here the question is, what is or should be, and these are not going to answer, this minimum number or isolated singularities which are not isolated complete intersection singularities. Okay. So that's there's not one answer. Let me say a few words about that. For example, for n equals 1, which is the n is the dimension of let me take a germ of dimension n. If n is 1, there's a definition. Oh, well, let me repeat. In all dimensions, when it's an isolated complete intersection singularity, we have a middle fiber that has the homotopy type of a bouquet of spheres of middle dimension, and the number of spheres is by definition the middle number. Now, when it's not a complete intersection, what should be the middle number? So, for example, this was studied time ago by very likely I'm going to make a mistake, Bushfights and Droyer. So when the empty space has dimension 1, and they give a definition that I will give it for those who understand, it's a number. They define the minimum number, let me say the G, by the dimension by d of omega 0 and d comma. Okay. This is at the point, this is a certain module which is very famous, very important. It's called the dualizing module of Grothendieck. And inside it, you have this, which is, what is this? Is you take the holomorphic functions, and for each function, you take the differential. So these are one form. Okay? This, so you take this quotient, that gives you something, you take the dimension, and that is what they call the minimum number. So what? Well, many nice things. One very nice property of this. First, if the singularity happens to be a complete intersection, this coincides with the usual minimum number. And two, if the singularity happens to be what is called smoothable, smoothable means that you have something like a minimum fiber, that you have a family of smooth one-dimensional manifolds that degenerates to the singular one. If the singularity is smoothable, then this is essentially the only characteristic of the smoothing. So you say, this last sounds very nice. We should try to get something like that in no dimensions. Yes, but there's one problem. When you go to dimension 2, you have singularities that, first of all, not all singularities are smoothable. But then it's even worse. In dimension 2, you have singularities which can be smoothed in many ways, and the corresponding minimum fibers have different Euler characteristics. So if you are going to have a minimum number that gives you the Euler characteristic of the smoothing, then of which smoothing if you have many. So there are troubles. Then yes.
Do they give example for this?
Yes, they do. They do many computations, explicit computations. Okay, so to propose to give a candidate let me introduce a candidate for a minimum number, which surely is going to be a nice candidate in some ways, and surely is not going to be nice in other ways. So it's one candidate. Let me introduce another index. Isolated singularity germ, okay? Let small v be a continuous vector field on V, singular only at V. Let V rad be a radial vector field. So you have the singular variety, and we know it has a local conical structure. So look at the intersection with a small sphere and take a smaller sphere. Okay? And now look at this radial vector field restricted to the small, the intersection of V with a small sphere. And now here you have your vector field that you don't know how it looks. Whatever vector field that has an isolated singularity here. We want to define an index for this one. For this one, we can define an index which we can call the radial index. And for the radial index for the radial vector field is 1. Why 1? Because that's the only characteristic of this point. There are other reasons. That's a simple reason. Now, what is this radial index for this vector field? If you look here, you are away from the singularity. This is just a cylinder. This is the link. This is the link times an interval. Isomorphic to that. Okay? It's a manifold with boundary, one component here, a couple of the link, and another component here, which is another couple of the link. And you have a vector field here, which is this radial, and a vector field here, which is your given vector field. You can extend that to the interior, we isolate the singularities. Then you define the radial index of this one to be 1 plus the Poincaré-Hopf index here. Very simple definition, elementary, nice. Okay? That definition is called the radial index. This is the radial index. We also call it the Schwarz index. I will speak more about Schwarz indexes tomorrow. This is something, this comes from Marilyn Schwartz's work in the early 60s, where she was working towards giving a definition of Chern classes for singular varieties. And what she did is very interesting. I will speak about that tomorrow, and it's much more general. In this very special setting, what she did was very particular. She was only considering radial vector fields. She was not bothered about more. And okay, but then this definition of the radial index, in different words, but the same definition, was introduced by Henry King and David Trotman in the 1992 preprint, which, for those who complain that your papers take too long to be published, this 1992 preprint was finally published this year. Good. So I want to see who beats that. Okay. Okay. So we'll do introduce it. But then later, independently, about the same time, in 1997, more or less, Evelyn and Hussein, Seade, and Marcelo Aguilar, Berkowski, and myself, who studied the same thing by different definitions in different contexts and so on. And in the notes I gave, I mentioned some of reference to Evelyn and José Seade. They have done a lot more about this radial index. And in my book with Braceleta Sugo, we speak about these things. I will not say more, just that this definition. But just one interesting thing. This proposition that V times ISIS. And V, a continuous vector field, and V with isolated singularity. Then the minimum number of V is equal to -1 to the n times this Schwarz radial index minus the GSV index, independent of the vector field. Okay? Now, this guy is only defined for complete intersections. This is only defined for complete intersections. This is defined always. And this coincides with the homological index, which is defined always. So you can take this minus this, and here you have an invariant of vector fields, which is defined always, and which for complete intersections gives the Miller number. So it's interesting to study, I think, this invariant. And I think I can stop. So just not focusing, just let's say, tomorrow I will come to study the Schwartz classes for singular varieties. That's a generalization of chain classes. And it's very interesting, I think.
On Friday?
Sorry, on Friday, yes.
So, questions?
An example of variety that is not mutable.
Yes, many. For example, take a holomorphic line bundle over CP1 with chain class smaller than -2. Okay? I mean, it cannot be simple because if you write it very simply, then those are always movable. It has to be something not obvious. So, let me tell you the following. If you have any Riemann surface and you take a line bundle over it with negative chain class, then you can take the Riemann surface, collapse it to a point, and you get an isolated normal singularity beauty. Okay? Always. So any Riemann surface, a line bundle with negative chain class, you can blow down the Riemann surface to a point and you get an isolated, you get a two-dimensional surface with an isolated singularity. Now, in many cases, those are hypersurfaces or complete intersections or smoothable. But I think that if you start with a line bundle of chain class smaller than -2, I think those are never, certainly those are never complete intersections, and I think they are non-smoothable.
An intuitive idea is that closed you don't have like the Milnor fiber.
Yes. Yeah. Now, if you want for obvious examples, let me tell you something. When this theory of smoothing started, people thought that all singularities were smoothable, and they were trying to prove that for some years, and they couldn't because it was false. Okay, and then somebody came with a trivial way of showing that it was a counterexample of singularity, and the counterexample was very beautiful. If you have a singularity and it's smoothable, it's a counter singularity, it means that you have a family of manifolds that degenerate to that one. Okay? If you have that, then the boundary of this, the link of the singularity, is the boundary of this manifold. Okay? That means that the link can be equipped with what is called a weakly complex structure in which it represents 0 in complex covorticity. And then someone showed, and they say it was Reneton, gave an example of a singularity in which the link cannot represent 0 in complex covorticity. So that singularity cannot be smoothed. Okay, but this is very beautiful, very deep. And it was an article signed by XXX.
Other questions? No? Okay, so we will continue on Friday with José Seade's lecture. And now in 5 minutes we will have